Okay, welcome to this final little section and I'm going to split this video into two. So there are going to be two videos here where we sort of bring everything together from over the last few videos and previous topics, just to show what sort of things can come up in exams. Okay, now the title, as you can see, is Forces and Braking. So we're focusing on here the forces involved and accelerations and energy transfers when objects brake, so normally road vehicles, trains, things like that. Now you've talked about this before in previous topics, but now we're going to use some of the formulas and ideas that we've talked about over the last couple of weeks and apply those into this situation. So the first thing just to remind yourself of really is, well, how do brakes work? Why do brakes stop vehicles? And the answer is just that brakes transfer kinetic energy into thermal energy. And they do that by doing work. So brakes do work, they transfer energy. Remember, work done is just energy transferred by a force. And the force here is friction, and that transfers the kinetic energy of the car into thermal energy. Brakes get really, really hot. And actually, you can find videos online of cars driving along, race cars, and their brakes are actually glowing red hot because of that energy transfer. So let's look at then a first example here. Okay, so in this example, we've got a car of mass 1,500 kilograms traveling at 30 meters per second, and it brakes to rest in 67.5 meters. Calculate the average braking force applied. Okay, if you want to give that a go and pause the video while you do it, that would be a good idea, and then we'll go through and see what we get. Right, I've just rewritten the question there because I obviously need to be able to write. I just thought I'd show you the picture. So then we can imagine, so here's our car and it's driving along. Oh, it's meant to be a police car. Right, give me a second. There we go, much better. So here's our police car. It's driving along and it brakes to rest, and it's taking it 67.5 meters before it has stopped. And we've got to work out the braking force. Now, I'm just going to put that up there. Now in the exam, obviously, it's really important that you are very careful with your formulas. Think carefully about what it is you are looking for. Now, we're trying to find the braking force. This idea, though, that we wrote down a minute ago is going to be really, really important. So it's transferring kinetic energy to thermal energy by doing work. So the amount of work done by the brakes has got to be the same as the amount of kinetic energy which our car had at the start. Right, because all of that kinetic energy has been transferred by the brakes doing work. So probably a start point here would be to work out the kinetic energy. Now, this is why knowing your equations is going to be so important, because you just have to keep coming back to them. So kinetic energy, half times mass times speed squared. Hopefully you can remember that one. If you can't, I recommend going back and watching the video. And so in this case, that's going to be half times 1,500 times 30 squared. So we'll simplify this then. Half times 1,500, that's 750, times 30 squared is 900. So we need 750 times 900. So the answer we get there is 675,000, and the unit, it's energy, joules. Okay, so that's the amount of kinetic energy that our car has got. Okay, so now let's think about how we are going to actually find the distance, we know the distance, how we're going to find the force applied. It's going to be using this idea. That kinetic energy must be the same as the work done. Okay, I've just moved that up a little bit. So we now know then that the work done must also be 675,000 joules. Because this kinetic energy has been transferred by the brakes doing work. Okay, so these two must be the same. So then let's go to our formula for work done. Work done, hopefully you can remember, is the force times distance. So work done, 675,000. Force, well, that's what I'm trying to work out. Distance, it tells me 67.5 metres. Okay, so that means then that the force, I'm just going to have to move this up a little bit more. That means that my force, if I divide both sides by 67.5, is 675,000 divided by 67.5. You can just about see that. Okay, and if you work that out, you hopefully can see that the answer we're going to get is 10,000, and the unit, it's a force, newtons. Okay, so there's our first example done. That would definitely be probably 5 marks in an exam, because you've had to notice that you're transferring the work done must be the same as the kinetic energy. Now, what it would be a good idea for you to do now, I'm going to just put up actually a few statements with some words missing. If you're watching this for the first time in order to make notes, my suggestion is that you now pause the video, copy those 4 bullet points out, and fill the gaps in. So this is essentially what we've just talked about, but then adding a couple of points on the bottom which the exam boards specify you need to know. Okay, let's go through then what those answers should be. So, when braking, the brakes do work to transfer energy from, and we said this earlier, kinetic energy to thermal energy. I will put all these answers up in a second. So the faster a vehicle is going, the more kinetic energy it has. So the more work must be done to stop it, hence a larger braking force is needed to make it stop in a certain distance. So if you've got more kinetic energy, more work needs to be done. Therefore, you're going to need a bigger force if you want to stop it in a certain distance. Or you could say that if you've got the same braking force, you're going to need a much longer distance to stop your car. Okay, third bullet point. A larger braking force means a larger deceleration. Okay, if you've got a bigger force, you've got therefore a bigger deceleration. Okay, the final bullet point then. Large decelerations may be dangerous as they may cause brakes to overheat. If you think about it, if you've got large decelerations, therefore, because of the large force, you've got a lot of work being done, and therefore the brakes can get really hot. If you actually look or measure the temperature of brake discs of a car after braking, they will have increased in temperature quite a lot. So it is important that you don't have too large deceleration because you get this overheating. And in fact, that's why racing cars don't have standard brake discs. They'll have brake discs made of a material that can withstand a much higher increase in temperature. So there are all those answers that we've just had. If you wanted to check what you've written, if you were filling them in as we went through, those are the answers that we had. Okay, right, another example now then. Here you can see, I'll give you a second to read it and maybe write it down. So a car travelling at a typical speed makes an emergency stop to avoid hitting a crocodile in the road 25 metres ahead. Estimate the braking force needed to produce this deceleration. I mean, it's an everyday occurrence there, driving along, suddenly there's a crocodile in the road and you need to be able to stop. Now, if this was an exam question, all right, it probably wouldn't be about a crocodile, but if this was an exam question, there are a few things that you'd need to notice in order to answer it. The first thing, and it is in bold there on the slide, is the word estimate. So you know that there is no absolute right and wrong answer. You are just estimating what the force needed is. So the sort of thought process that you need to do is be thinking about, well, what do we know? What are we trying to figure out? And therefore, what sort of, or what equations are we going to be using? Okay, so here's the situation, driving along, here's our police car again, driving along, and then suddenly, 25 metres away, there's the crocodile, and we need to stop. Now, the only information you were given in that question is this 25 metres. So let's think about what we actually know. So we know the distance that it's taking to stop here, and we do know that it's stopping. So therefore, actually, we know that the final speed of our car here, our truck, is going to be 0. And it does use the phrase a car travelling at a typical speed. Now, if you think back to the motion topic, we actually talked about typical speeds for different vehicles. And a typical speed for a car, you remember the typical speed for a car, was about 25 meters per second. Okay, and so actually, we do know roughly what the speed of the car is. We know that the distance it's going is 25, and we do also know that the final speed of our car is 0. So if you think back to all the formulas that you've looked at, we've got distance, we've got initial speed, we've got final speed. So from that, we could work out the acceleration of the car. Now, ultimately, we're after force, but we do then have a way of linking force to acceleration. So let's go with that. Now, this is one of those equations which is given to you on the formula sheet, and it's that really long one. So I'll start over here. Okay, remember that one? Final velocity squared minus initial velocity squared equals 2 times acceleration times distance. Sorry, you can't quite see the start of it there. Okay, let's put some numbers in then. Well, the final speed or velocity we know was 0. So we've got 0 squared minus initial velocity. Well, that was about 25 squared equals 2 times acceleration. That's what we're trying to find at the moment. Times distance, which is 25. Okay, this is a good recap then of how we actually answer questions like this. So 25 squared, that's 625. 2 times 25 is 50. So we've got 50 times acceleration. Okay, so what this will then tell me is that acceleration, we divide both sides by 50, is minus 625 divided by 50, and that gives me an answer of minus 12.5, and remember the unit for acceleration, meters per second squared. Now, what we can now do then, we're not trying to find acceleration, we're trying to find the force. But hopefully you can remember another equation that links force and acceleration. And it was Newton's second law, this one. Force equals mass times acceleration. Now, you're not given a mass. However, the word estimate was in the question. So therefore, we just need to estimate a very, very rough mass for a car. Now, you're not expected to know this in detail, but you should be able to just come up with a rough estimate. So for a car, the mass is going to be in the region of, and in fact that symbol there means on the order of, so very roughly 1 ton for a car, which is 1,000 kilograms. So if we use that then down here, we're looking for the force. Mass is 1,000. Acceleration we just found was minus 12.5. Now all the minus tells us it's in the opposite direction to the direction it's moving in. So I'm just going to put 12.5 in to get our answer. So that gives me 12,500 newtons, and that would be my answer. Now obviously you might have estimated very slightly differently. You might have said 1,500 kilograms and you'd have got a different answer. But as long as you are in the right region, the right ballpark, you'll get the marks for that. Okay, so hopefully you can see here how we're using all our equations, bringing them together. And in the next video, the second section on this, we'll carry on looking at how we can apply these ideas to look at braking, stopping distances, and things like that.